A rocket gets lighter every second it burns. A railroad car catching rain gets heavier as it rolls. Newton's second law, in the familiar form force equals mass times acceleration, quietly assumes the mass never changes. In this video, we set up the tool that handles flowing mass and sort every mass transfer problem into 4 categories. So far, every system we analyzed was built from discrete, point-like objects, each carrying a fixed amount of mass. Now we broaden the view to systems where material flows between the objects. Picture coal falling from a hopper into a moving railroad car, or sand leaking out of a railroad car, or grain being blown forward into a railroad car, or fuel ejected from the back of a rocket. In every one of these cases, material continuously streams into or out of an object, so the object's mass changes as it moves. The starting point is the momentum principle. The total external force on a system equals the time derivative of the system's momentum. F sub s equals dp by dt, where p is the momentum of the entire system. When the mass is constant, the derivative of mv is mass times the derivative of velocity, and the principle reduces to the familiar force equals mass times acceleration. But the momentum form is more general. It stays true when mass flows between the parts of a constant mass system, and it is the version we use throughout this chapter. Here is the strategy for every mass flow problem. Analyze how the momentum of each piece of the system changes over a small time interval from t to t plus delta t. Then take the limit as delta t goes to 0. That limit evaluates the derivative explicitly. The total external force equals the limit as delta t goes to 0 of delta p over delta t. Written out, the system momentum at time t plus delta t minus the system momentum at time t all divided by delta t. One quantity demands special care. Delta m, the mass of material that flows into or out of the object during the interval delta t. Every mass flow problem begins by identifying it. Every mass flow problem falls into one of 4 categories, sorted by whether the transferred mass delta m carries momentum. Category 1. Mass flows in but brings no momentum. Rain falling into a rolling car. Category 2. Mass flows out but takes no momentum with it. Sand leaking from a gliding skater's back. Category 3. Mass flows in and carries momentum, impelling the object. A fire hose driving a boat forward. Category 4. Mass is ejected and carries momentum away, so the object recoils. Fuel leaving a rocket. We take these one at a time. Category 1. Rain falls straight down with speed u into a car of mass m rolling forward with speed v on a frictionless surface. Watch one small parcel of rain, delta m sub r. It falls vertically, so its velocity has no component along the direction the car moves. It carries mass into the car but 0 forward momentum. The car's mass grows, yet the rain contributes nothing to the momentum in the direction of motion. That is the signature of Category 1, a transfer of mass into the object with no transfer of momentum along its motion. Category 2. An ice skater glides across the ice at speed v, holding a bag of sand. The sand leaks straight down relative to the moving skater. Each small parcel, delta m sub s, leaves the bag falling vertically in the skater's frame, so it takes no momentum away from the bag along the direction of motion. Draw the scene in 2 reference frames. In the frame fixed to the ground, the leaked sand still moves forward at speed v. It keeps the forward momentum it already had, and simply stops being part of the bag. In the frame moving with the skater, the sand drops straight down. Either way, the departing sand carries away no momentum relative to the skater. Mass leaves the bag. The skater's forward speed does not change. Category 3. A fire hose shoots a horizontal column of water at a burning boat of mass m sub b. The water moves at speed u faster than the boat, which is already gliding forward at speed v. During each interval, delta t, a column of water of mass delta m sub w strikes the hull. This time, the arriving mass carries forward momentum and it delivers that momentum to the boat. The impacts continually drive the boat forward, increasing its speed. Mass flows in and the momentum flows in with it. That is what impels the object. Category 4. A rocket of mass m sub r ejects fuel of mass delta m sub f from its back at speed u relative to the rocket. The ejected fuel carries momentum backward and the rocket recoils forward. Draw this in two frames. In the reference frame of the rocket, the fuel streams backward at speed u, while the rocket picks up a small forward recoil speed, delta v sub r. Now draw it in a frame where the rocket is already moving forward at speed v sub r. After the ejection, the rocket moves at v sub r plus delta v sub r, while the fuel ejected backward moves at speed u minus v sub r, since the exhaust outruns the rocket. Same physics, two descriptions. Mass leaves carrying momentum, and the object recoils. This is how a rocket accelerates in empty space. In all four cases, the procedure is the same. At time t, carefully identify the momentum of the object and the momentum of the transferred material. Together, they form the system momentum at time t. Then do it again at time t plus delta t, object plus transferred material, giving the system momentum at t plus delta t. The difference between the two divided by delta t is what the momentum principle equates to the total external force. Here is the crucial subtlety, and the point this whole chapter turns on. When we defined the momentum of a system, we assumed the system's mass stays constant. So the transferred material belongs to the system at both times. At time t plus delta t, you cannot drop the sand that has already left the bag. It is still part of your system wherever it is. And at time t, you must include the rain that has not yet landed in the car. The system boundary follows the mass, not the object. Choose the system once and keep every bit of that mass inside it at both instants. Let's put the whole strategy to work on a worked example, filling a coal car. An empty coal car of mass m0 starts from rest, pulled along the track by a constant applied force of magnitude F. At the same instant, coal begins to run into the car from a hopper at rest above the track at a steady rate b. So after a time till coal mass of b times t has fallen in. Find the car's speed at the moment a total coal mass m sub c has been transferred. First, classify the problem. The coal falls vertically from a hopper at rest, so it arrives with no horizontal velocity, and it transfers no horizontal momentum to the car. This is category 1, mass in with no momentum in the coal version of rain falling into the rolling car. Next, choose a constant mass system, the empty car together with the entire coal mass m sub c that will be transferred. With that choice, nothing enters or leaves the system. The coal merely moves from the hopper into the car while staying inside the system the whole time. We track momentum along the horizontal direction, which we call the x direction. The initial state at time 0 is the empty car at rest before any coal has arrived. The coal still sitting in the hopper has no horizontal velocity, so the x component of the system momentum starts at 0. The final state at time t sub f is when all the coal has been transferred, so m sub c equals b times t sub f. The loaded car of mass m0 plus b times t sub f now moves at the final speed v sub f. The x component of momentum in this state is m0 plus b times t sub f all times v sub f. Now apply the momentum principle in the x direction. The impulse of the external force equals the change in momentum. The integral of f from time 0 to time t sub f equals the final momentum minus the initial momentum. The force is constant, so the integral is simply f times t sub f, and the momentum principle becomes F times T sub F equals m0 plus b times T sub F, all times V sub F. Solving for the final speed. V sub F equals F times T sub F divided by m0 plus b times T sub F. And since m sub c equals b times T sub F, the transfer takes a time m sub c over b. So in terms of the coal alone, V sub F equals F times m sub c divided by b times the quantity m0 plus m sub c. Read the result. The numerator is the impulse, the force delivered over the transfer. The denominator is the full final mass, the empty car plus all the coal. The falling coal added mass but no forward momentum, so the same impulse must move more mass, and the loaded car ends up slower than an empty car pulled for the same time. The entire effect of the mass flow sits in that denominator. Here is the toolkit this chapter is built on. The momentum principle, total external force equals the rate of change of system momentum. The strategy, track the system momentum from time t to t plus delta t, then let delta t go to 0. The classification, mass in without momentum like rain into a car, mass out without momentum like sand from a skater's bag, mass in with momentum like a fire hose driving a boat, mass out with momentum like rocket exhaust. And the rule that makes it all work. The system's mass must stay constant, so the transferred material is counted at both instants, wherever it happens to be. In the problems ahead, each of these 4 pictures becomes an equation of motion, with the rocket the most famous of all. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.